Right, hello. I want to talk about GCSE Mathematics in a manner that's similar to the way I would talk about it in an introductory lecture to an actual course. So this introductory lecture might take one or two sessions. But where I talk about just an overview, so I ask students to take in as much as they can, but I try and just give an overview, and then obviously later on we'll go into the subjects in more depth. So, having said that, I also should say that rather than doing it all in one go, I'm going to split it down into nice little chunks. So, starting right from the bottom, I've got integers here. Now, the reason I've written that down is obviously, well, one of the advantages is that students sometimes don't actually understand or don't know how it's pronounced. So, it's pronounced integers. And it's just the straightforward numbers like this. So you've got those straightforward numbers like 1, 2, 3. But it also goes the other way. So you've got 0, minus 1, minus 2, and minus 3. And the next step up from integers is the rational numbers. The name rational comes from ratio, implying a fraction. But you've got to be a bit careful here. Rational numbers and fractions are not the same thing. The exact definition is that rational numbers are fractions where the top and bottom are integers, or to be more mathematically precise, where the numerator and the denominator are integers. So these are both rational numbers, but this one isn't. This is a fraction, but it's not a rational number. There's a bit of a rider to this. If I say something like 3 over 2 over 7, that at first sight that's supposed to be a 2. That first sight might not look like a rational number according to my definition, but I can rejig this to be 3 over 14 using methods we'll talk about later on. But that is now a rational number. So that, although it doesn't look like a rational number, that is in fact such a thing. Whereas this, I can play around with this as much as I like, but I cannot get it into the form where the numerator and the denominator are both integers. So that is not a rational number. Right. So the next step is to show, well, actually before that, if I write a rational number, say, I don't know, 3 over 4. Now this is a fraction and a rational number, but it also has the purpose of a division. I can view that as being 3 divided by 4. Likewise, 9 over 2. That's as a fraction, or it can be considered as a division. So 9 over 2, that is equal to either 4.5 or 4.5 or whatever you like. So it's got this dual purpose, and you'll find that the more you get into mathematics, this will be the form that a division is presented as. So you might be aware of the that type of form. But overall, you'll probably tend to use this form to denote a division. The more you get into mathematics. Now. What I want to say now is that integers are in fact rational numbers, and it'd be like this, not to scale, but those are the integers, and those are the rational numbers. All integers are rational numbers. So I mean, how am I going to show this? So say I take 9. Now, following on from what I just said now, that can be represented as that, like that. How do I know that? Because I can treat that as a division. I mean, this is a bit of a hand-waving explanation, but treating that as a division, if I've got £9 and I divide that out among one person, then everyone will get £9. So 9 over 1 is equal to 9. So in that sense, you can see hopefully from that an integer is a rational number. This fulfills the definition that I gave for a rational number. So what use might that be? I mean, one use could be in multiplication of fractions. say I've got something like 3 over 2 No, I'm getting confused with what I've just done now. So, not a division, a multiplication. How do I tackle something like that? I mean, perhaps before I talk about that, talk about fractions in general. Say I've got 3 over 4 times 5 over 6 or something like that. Now, I think we're dealing with arithmetic operations on integers. Arithmetic operations on fractions. First thing to realise is that there's two separate operations here. There's an operation for multiplication and division, and there's a totally separate one for the addition and subtraction. Having said that, with the division, there's a sort of a bit of a fiddling around beforehand to convert it into a multiplication. But within that scope, the multiplication and division rules are the same, more or less, which I'm just going to show now, but be aware that they are totally separate from the rules for adding or subtracting fractions, which I'll talk about later on. Second thing is that in mathematics it's quite common for a rule to be stated, and you learn the basic rule, and once you've learned the basic rule and as to how things work, then you can sort of modify it later on, and this is going to be the case here. The basic rule when you're dealing with multiplications, the rule that will always work is that you multiply right across the top and you multiply right across the bottom. So 3 times 5 equals 15, 4 times 6 is 24, and that will always work. Where the modification comes in, which we'll talk about later on, is that that would not normally be accepted as an answer, because you normally accept an answer to its lowest terms. By that I mean you look at an answer and say, is there a common factor to both of those, and can I reduce them further down? And stated quickly, I can look at that and realise that the top and the bottom here has a factor of 3. So I can alter a fraction. Again, that's an important rule, is I can alter a fraction by dividing the top and the bottom by the same number. Likewise, I can multiply the top and bottom by the same number as well. The numbers change, but the actual fraction represents the same number. So if I divide the top by 3, that'll give me 5. Now if I divide the bottom by 3, that'll give me 8. And I look at that and I say, is there a number that will divide top and bottom, so I can reduce this even further? And basically the answer is no. That is the fraction in its lowest terms, and that would be the answer to this particular multiplication. So how might that help this particular situation here? Well, what I do is I convert that into a fraction. So it's 3 over 2 multiplied by 7 over 1. Okay, 7 is an integer, but it's also a rational number represented in this manner here. So again, multiply right across the top, 21, multiply right across the bottom, 2, and that is actually the answer in its lowest terms. There is no number there that will divide both the top and the bottom to give integers. So that is the actual answer to that multiplication. Right, now go back here. When I'm dealing with the when I'm considering the decimal form of a rational number, then there are numbers that are exact. Like there's say a half is equal to 0.5. and a quarter is equal to 0.25, and those are exact. The 0.5 is exactly equal to a half, 0.25 is actually exactly equal to a quarter, but others in general are not so exact. I mean, the best one known is a third. that is equal to 0.333 recurring. And you can see there's a certain amount of, the way it's presented here, there's a certain amount of error here. So I mean, I can state, it's the same for all these, so I can state right at the bottom level, or right at the beginning I should say, that resist the temptation, as many students do, to so automatically reach for the calculator and get an expression out like this. You know, mostly if you get an answer out as a fraction, then that will be the exact answer, that will be the answer you're after. You can see what I'm saying here is that if you have a third and you just try and write that down, then that is not the correct answer. That is an approximation, and it gets even worse if you just say, okay, 0.3. You know, that's obviously going to be in error with respect to 1/3. Now, I should have stated more clearly actually that recurs, and that'll be the case for all rational numbers, that they do recur to a certain extent. Well, not to a certain extent. I mean, they do recur, but some are more obvious than others. That's more obvious, and I can represent that more mathematically like that. Now, this one recurs. I don't see if I can fit it in. 5, 7, 1, 4. I'll have to put it down here. 0.5, 7, 1, 4, 2, 8. Yeah, and then it recurs again, and I would denote that as something like that. That will be just like the other one up above. That will be 0.27, so it'll be like that. Now this one doesn't recur immediately, but it does eventually, so it'll be 0.46, like that. So what I need to stress here, you know, just to lead on from what I've just said here, that if you get that as an answer and you put that down, even if you put the dots in implying that it goes on forever, that will be wrong, and that will be marked as wrong in an exam. There is a thing in the GCSE which sometimes you get an expression called ISW. That means ignore subsequent working. So So if you put a third down, that is the right answer, and then you wrote this down, then although this is wrong, then you would just be ignored in that case if it's ISW. But don't rely on that being 100% the case. Again, for completion, this form here would actually be correct. If you put that down as an answer, that would actually be correct. For reasons that I can't really explain in full here. But the point is, really, why bother? If you get that as an answer, why bother to go to the extent of putting these down, that down or that down instead of that, and so on? It's just a total waste of time, And I need to stress this also because in my experience, even A-level students get this wrong. They're trying to get a proportion out from a Venn diagram, and instead of sticking down a fraction, they stick down. Well, if instead of sticking down a fraction, they put this down or this down, that would be marked correct. Although to my mind, that would be very, very unusual. Instead of sticking this down, instead of just saying 1/3. But quite definitely, if they put this down and that down only, that would be marked wrong. The next step from there would be to the irrational. So do I need to write it down? Irrational. So classically, these are numbers like pi. Pi equals COD, and you also get as number I've just met before, √3. These are irrational numbers, and I should say that pi is representing the circumference of a circle divided by its diameter. Now these are irrational numbers, so you can't actually represent them as a fraction. Pi is approximately equal to 22/7. It's not exactly, quite commonly in questions they'll say, okay, approximate it by this. But the thing is that you can't represent pi exactly by a fraction. And leading on from what I just said about recurring decimals for rational numbers, these irrational numbers, when they're represented as decimals, they have no pattern at all. So in that sense, it might, in a hand-waving way, you could say that they can't really be represented by decimals either. So it's this quite funny situation of numbers which can't really be represented by fractions or decimals. I'm talking in a very, very hand-waving way here. But again, you probably know this, that pi, nowadays they get supercomputers representing the decimal equivalent of pi up to some massive number, and that's because there is no pattern there. They can only just do it by computer and see what comes out. There's no pattern to predict what the form of the decimal representation is. I mean, I once sat through a session where someone read off from memory the first 1,000 digits of pi, which was quite very, very boring, but at the same time quite fascinating. But that's the whole point, that it is a great memory test to do something like that, list off pi to an enormous number of digits, basically because there is no pattern. So that's probably really all I need to say. All I want to say for the first session. I mean, there are all kinds of funny things you could say about this. That you square that and it still remains as a irrational number. But something like root 3. If you to square that like that would be 3. So you'd have an irrational number, but when you square it, it becomes an integer which has more normal forms, if you like, putting normal in apostrophes. Having said that, one thing I should say is that most square numbers are irrational numbers. Obviously you get something like square root of 4, which is 2, and square root of 9, which is 3. So they're quite normal. Again, using this sort of normal in apostrophes, they give out integers. But anything else apart from these types, root 3, root 5, root 7, root 11, and so on and so on. These are all irrational numbers. So anyway, as I say, that's okay for first session. Thank you very much if you're still with me, and hope to see you for part 2. Thanks very much.